Our next speaker is Tony Trim. Jerry Harris will be introducing Tony Trim. Thank you.
Alrighty. Um, Good evening, ladies and gentlemen. I have the esteemed honor of introducing one of NSBE's own, Tony Trim. Let me tell you a little bit about him. Ladies and gentlemen, it's an honor. Basically said it already. An esteemed digital strategist and IoT solution architect with over 18 years of experience in the oil and gas industry. Tony's technical proficiency encompasses control system automation, data mining, and edge IoT ecosystems. He has a stellar track record in efficient, efficiently managing large-scale projects, meeting budget concentrates, and uh, and adhering to timelines while exceeding client expectations. Tony is also adept to implementing machine learning applications, ensuring seamless system integration, and driving digital transformation through SAS models. As director of the as director of the National Society of Black Engineers Information Technology, yes, sir. We gotta love the NSBE members. Think think tank special interest group. He patiently fosters innovation and collaboration within the IT community, bridging gaps between corporate America and IT professionals. Tony Trim's expertise and commitment to progress are commendable assists in the technology realm. Ladies and gentlemen, without further ado, I present to you Tony Trim. And from one computer engineering tech to another, from one computer engineering tech to informational tech, I really want to hear this. Thank you so much, Tony.
I'm glad to be here. And the interesting thing is that this presentation, I don't know how you all are going to take this, but there's not going to be any math. I watched the last two and I realized I forgot to, put the math in this thing. So I apologize now. I'm sorry. I kind of left it out. And I'd be remiss if I know there are a lot of people in graduate school. Potentially, there may be some undergrads here, or there may be some professionals here as well. So I do, and I do have to put just a small plug in, just real quick, just because Eden is a employer of a lot of NSBE professionals. So, and I just want to give you just a little insight of what Eaton does as a whole. And Eaton does do a lot for the industry as a whole. So Eaton is an intelligent power management company that is involved in every aspect. Basically, we make what matters work, right? So we provide products in oil and gas, which is my first love, 18 years in it, aerospace, commercial and residential construction, renewable energy, Department of Defense, transportation, mining, metals, pulp and paper, pharmaceuticals, chemicals, and automotive, just to name a few. And for the car buffs, Eden even makes superchargers. So it's an interesting company. And once you graduate, I'd recommend giving it a shot. Moving forward, asset performance monitoring, the unified strategy. So you see my imagery of like, being in space on the top, and then you see like being down here on Earth, and you're wondering, okay, what does that mean? So let's talk about asset performance first, right? So asset performance management is really an ISO standard, and to be specific, it's ISO standard 55,000, which pretty much um, it examines the value of asset management and the scope of asset management uh, system, strategic asset management plans, asset management decision making, risk management, finance and asset management, and the scalability of asset management systems. So now you're thinking about, okay, the unified strategy, how? Well, APM, asset performance monitoring and management, is more than a standard or even a technology. It is a strategy that unifies energy, process improvement, and my first love, information technology, to work together towards operational excellence. So let's see how all that works together. Let's see. All right. The four pillars of analytics, right? So let's look at it. First thing we have is descriptive analytics. What happened? All right. So imagine descriptive analytics is basically just showing you what it is. Imagine you step on a scale, the scale tells you how much you weigh. That's just what it is. Next thing, diagnostic analytics. What, why did it happen? So imagine you step on a scale, you look at a BMI chart, or you step on a scale at the doctor's office, your PC, your primary care, and they tell you, okay, based on your BMI, that's kind of gives you the diagnostic of yourself, based on your height, weight ratio, whatever, right? Of kind of how you're doing. So that kind of gives you the diagnostic of yourself. And I have a quick little video here because, I grew up kind of being a Star Trek buff, right? So let me know if you can hear this when it comes up.
We cannot hear that, Tony.
Oh, you can't?
No, we cannot.
You can't hear it?
No.
Well, okay. Well, I'll give you a quick synopsis of it. Well, in Star Trek, one thing that they always said that I always noticed was they were always running level 1, 2, 3, 4, 5, diagnostics on everything. So had you heard it, you would have heard them going through the whole quip of going through different diagnostics, different things. And it seemed kind of cute to me when I saw it, but we'll move on. So let's see. Predictive analytics. All right, that's the next pillar. What will happen? So let's go back to the scale situation. So you step on a scale, and let's say this is a electronic scale, right? Let's say it's a yeah, let's say it's a electronic scale. So you step on the scale, it tells you how much you weigh. And let's say this scale has like a database, right? So you step on the scale, it tells you how much you weigh today. It knows how much you weighed last time you stepped on the scale, right? And let's say it has a little built-in uh, linear regression, and based on that, it tells you that you're going to weigh you're either going in an upward progression or you're going to lose weight or something like that. Let's say it tells you that you're going to gain weight next time, right? So that's the predictive aspect of it. But then something even better, the next phase of it, prescriptive analytics. What can be done to prevent it from happening again, right? So now we're going to go a little further. So now this scale is getting real smart. Scale's getting real smart. So you're on the scale now, and you step on it. It tells you how much you weigh. It knows how much you weighed before. It knows what your BMI is. But this time it's talking to you. It's telling you, okay, it knows that on Tuesdays and Thursdays you eat donuts, right? So it says, okay, if you stop eating donuts on Tuesdays and Thursdays and you work out on Monday, Wednesday, and Fridays, if you do that for a year, at the end of the year, you'll lose 10% of your body weight. So by going through this whole example, you'll see how the four pillars of analytics we work through that to get to the final end of how analytics can work together to show you how they can work together to more or less work together. So if we go from descriptive, it showed you what happened. Diagnostic, why did it happen? Predictive, what will happen? And prescriptive, what can be done to prevent it from happening again? Oh, let's see here. Okay, now in the industrial space, we're looking at past practices, calendar based, and predictive, right? So in the past, we looked at we basically just let things run till they broke, right? We had we had unplanned downtime due to sudden failures. Outages lasted for days. No visibility into the system health, and the time and severity of the failure was unknown. Then we moved into calendar based. So we said, okay, based on what we think, we're going to replace this equipment at a certain amount of time. So every 30 days, we're going to replace this particular component. And that's what we did. So we replaced this particular component at a particular time. So with that, we had strategic uh, outages to mitigate the system failure. Um, we did upgrades, expansions, and to avoid, failures. Right now, the next failure is not known, but we were able to basically limit the amount of unplanned failures, or at least we thought we were. What we actually did was we increased the amount of planned downtime. Then we tried to get into predictive, right? So predictive is, predict a sudden failure outage. Now that's a little bit more difficult than we had anticipated, and we got more into anomaly detection. But let's move forward. Okay, so now digitalization. Digitalization kind of enables optimized maintenance. So we talked about, you know, run it until it breaks. We talked about preventative scheduled maintenance activity. We talked about proactive strategic actions aimed to reduce operational deficits. And then we talked about prescriptive, the insights to optimize system resilience and equipment health, right? And these are all things that you adopt when you go into predictive maintenance strategy or asset an asset monitoring program. Now, data-driven reliability. Now, no matter what the system is, whether it's a spaceship, whether it's an industrial plant, you always want to keep track of your KPIs. Now, if we look at this right here, we're looking at environmental systems, mechanical systems, electrical infrastructure. So, for example, with environmental systems, we're looking at temperature, humidity, pressure, gas leaks, fire systems. Mechanical systems, we're looking at HVAC, so that's the the air conditioning, the chillers. Uh, we're looking at the auxiliary equipment health monitoring, water, air, gas, steam, leak detection, vibration, oil, fuel levels. In the electrical infrastructure, we're looking at the typical voltage, current, power factor, power demand, UPS, battery monitoring, any other protected devices, and those all feed into the KPIs or the key performance indicators. Now, what that does is that gives us a single pane of glass to see our entire system, and that view is what lets us know on our operating efficiency, overall equipment excuse me, overall equipment effectiveness, or our OEE, um, even our environmental footprint, because that kind of goes along with our total energy consumption and our power usage effectiveness. Now, now, when you start going into data-driven reliability, your next question is, okay, what can it lead to? All right, so here's what it can lead to. All right, so edge and cloud computing. So you have data storage closer to the data source. All right, what does that do? It saves time and money. It uses networks of remote sensors online to store and manage and process data. So when you're looking at space travel or a unit in space, or those sensors being in space, right? If you have your edge devices closer to those particular pieces of equipment there in space, that helps out. Offers demand availability of computer systems resources without direct management by users. That helps as well. Um, Research and monitoring. So let's say you have research facilities among the stars, right? That way you can have ground control and space vessels can collaborate through better communication via insight and real-time solutions. You can have data monitoring in real time, which will allow astronauts to report details, right? You can also leverage that information for monitoring natural disaster phenomena using detailed findings from real-time data viewed from space. You can also accelerate research capabilities from pandemic to climate change. So another view, now if you flip that on the other side, right, let's talk about astronaut healthcare, right? So you can also leverage edge computing to monitor space travelers' impact on the human body. So you can go along with biometrics as well. So Data is shared in real time, which can help thwart bone density loss, changes in genetics, and many other health issues, that affect astronauts. Then, space agriculture. So computing can not only crunch numbers or saves lives, it can sustain life too. Data can improve the practice of growing food in zero gravity, um, or it can also optimize meals, healthier meals with fewer supplies, and other cargo for each trip. Now, the next thing is also what can it lead to? So let's look at spaceship design, right? The data derived from space computing can also provide insight into more efficient combustion, water purification, and engineering methodologies. We could, in essence, develop safer, cheaper, and more efficient spaceships. Um, the more data we have, the more innovation that's inevitably possible. Now, now data-driven reliability into the future. Now, this right here is where it kind of gets interesting, right? So, how do we do it with quantum computing? So, let's think about what quantum computing really is, right? So, I guess the general definition, which is right here, is computing is quantum computing is a technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers, right? So, why do we need quantum computers? We use quantum computers to solve problems where classical or binary-based computers struggle. Where are quantum computers used? Quantum computers are best used to solve complex optimization problems or simulate real-life systems. For example, synthesize a molecule and predict its behavior in the real world. So let's think about a few things here. So what's the difference between quantum computing and classical computing, right? Um, so with a classical computer, you have transistors. Now, granted, nowadays they're really, really small, but it works in the same principle. Classical computers have transistors which can either give you a 0 or a 1. Quantum computers have qubits that can give you a 0 or 1, but they say at the same time. When in actuality, it's not really at the same time, and it's more when you observe it more or less, and it's kind of interesting the way it works. And if I, how much time do I have? Yeah, I got a little bit of time. So if you can imagine, if you're looking at, let's use a golf example. Okay, if you can imagine hitting a golf ball, and that golf ball that you hit is going in every possible direction, but all those directions that it's going is going to be a hole in one. It's just taking different ways to get there. That's kind of how it's happening, right? But what really counts is that it's using the one that actually counts is the one that's optimized, the one that's optimized, I guess, that it sees as the best way of going there. And I guess a better example would be, if you remember, I don't know if there are any Marvel fans here, but if you remember Endgame, when Doctor Strange, was it Doctor Strange? Yeah, Doctor Strange was going through the whole scenario of all the different possibilities of what can happen. Whenever Iron Man was doing something with Thanos, and then he finally came back, and there's only one possibility that would work out well. That's kind of how it works with quantum mechanics in a way, and how the electrons work when they're, because they don't really do everything at the same time. What it is it looks at all the possibilities, and it finds the best one. And that's why quantum computers are really good at optimization problems, and they're really good at simulating real, real life systems, like simulating how a molecule would act in real life, things of that sort, right? So that's kind of how they act. Okay, so moving forward. So with classical computing, power increases in a one-to-one relationship with the number of transistors. Now with quantum computing, power increases exponentially in proportion to the number of qubits. So right now, the most powerful quantum computers probably owned by IBM, and I think it has somewhere between 400 and 500 qubits. And let's see. Um, Classical computers have low error rates and they can operate at room temperature. But if you look on this right here, most of the stuff on this in this picture right here is to keep it cool. These quantum computers had to be kept at almost like zero, like almost 0 Kelvin, pretty much, like really cold. Like they'd be kept ultra cold. And like I said, everyday processing is best handled by classical computers, and optimization problems and analysis and simulations are best handled by quantum computers. All right. So, any questions? Can you still hear me?
We can hear you. Thank you, Tony, so much for that presentation. You really pointed something out that is needed. As an engineer in every different field, we can use information that you sent and we can apply it, just not in space operations, I believe. But I come from automotive industry for last 10 years. I just am transitioning to aerospace. And what you have, go
Oh,
ahead.
you know what I just realized?
Mm-hmm.
I'm not done.
Oh, I was wondering.
Yeah, I'm
Continue
not
on.
done. You know
Well,
what?
you have time. Go ahead.
Yeah, I'm not done. I saw this. I was like, man, here we
Go
go.
ahead. There you go. I was
All
wondering. I
right.
was like, okay,
Okay.
thank you. Go ahead.
So here we go. So here is asset performance monitoring, the benefits of adopting data-driven reliability. So as you can see right here, you see like an industrial facility, right? So you have, all your processing capabilities right here. So and this is so for industrial application, right? So when you okay, let's talk about the Pareto rule, right? 80-20, right? So if you think about it, the big buzzword is artificial intelligence, machine learning, generative AI, all this great stuff like this, right? But 80% of the value that you get out of that type of thing is derived from just monitoring your equipment. If you just keep an eye on it remotely, like monitor it, see how it's operating, get some diagnostics on it, you don't necessarily you can get 80% of the value just doing that. Like for example, earlier we talked about the scale, right? If you just like keep an eye on your health, on how much you weigh, regularly, you're more prone to, you know, stay healthy, right? Like if you go to the doctor like you're supposed to, take your physical once or twice a year, you're more prone to be healthier than somebody that just, you know, doesn't do it. It's just the way it is. So if you just monitor your equipment, take care of it as needed. When you see something's wrong, take care of it. You'll reduce unplanned downtime by 25%. You'll reduce unexpected breakdowns by 60%. You'll reduce energy costs by 10%. You will improve energy efficiency by each asset by 2%. You'll improve reliability by 3%. You'll reduce the maintenance cost by 12%. And you will improve your operational efficiency by 7%. Just by monitoring all your equipment. And, so data driven reliability services a diverse market, right? You have oil and gas, semiconductor, pharmaceuticals, petrochemical, automotive manufacturing, even though they're on strike right now, but airports, transportation, it serves all that. If you just monitor what you have and take care of it as needed, a lot of time the predictive and the prescriptive, that's only 20% of the value. Because if you think about what it takes to do, and I know a lot of you all in this call are extremely intelligent and heavy mathematically focused. So you understand the complexity in doing predictive analytics. And you understand that you can't do a predictive model unless you have, labeled data that has failures that you can trend and feed your model to train it properly to so you can predict failures. Otherwise, and so the thing about it is a lot of these industries like oil and gas, they don't have the data there, or it's not labeled where they could sit there and build a model that says, you know what, this motor failed. Let's build a model because we have all this data. No, they don't have that data. You know, so it's best just monitor it, and after you monitor it for a while, then eventually you build that repository of data. And that's why I tell lots of customers that I visit is that give me 3 years to monitor your data. Within 3 years, I'll have a repository of data. I'll have anomalies that I can build an anomaly detection model. Once I build that anomaly detection model, I can flip that into a predictive model, and then eventually we could turn that into an optimization model. But it takes about 3 years. So if all that fails, now I don't know the age group of the crowd, but if all that fails, I do have this product that we also sell over at Eaton. It's called a flux capacitor. It takes 1.21 gigawatts. It also can use plutonium, but you have to put it in a DeLorean and you have to go 88 miles per hour. And it enables you to time travel. So what you can do is you go 88 miles per hour, and if you can go back in time and redo whatever you have to do, so whatever fails doesn't fail. So that's also an option. And you can also get the plutonium at actually the plutonium is not available at O'Reilly, so you have to call your local plutonium supplier. But yeah, now that's it. Hmm.
All right. Thank you, Tony. We really
Well, I guess
appreciate. Go
nobody
ahead.
got the joke, huh? Y'all didn't get the joke. That it was
I got.
no one's ever seen Back to the Future, huh? I guess I'm showing
I
my
think
age.
I was thinking though, like
guys.
at the plutonium store.
Okay,
I was when you played the Star Trek reference, I really got that. I would like to say I got it firsthand.
but nobody got the Back to the Future flex capacitor, DeLorean,
I
I
plutonium.
got
I
that one
was
too, for
wondering. I was
sure.
like,
Come on, that was fresh. You got to give me that one. That was
yeah, that
fresh.
was good. That was good. She got it. She got Jackie got it.
Yeah,
So that's fine.
1.1 gigawatts.
Oh, that's awesome. Thank you for making us laugh. So we really do appreciate the presentation.